So, let us try to finish this problem that we are working out. So, the pile that is
that cos alpha will be 2 plus s square. Root 2 by root over 2 plus s square.
square root of 1 plus 1 root over 2.
Yes,
So, actually you take approximately this square root. No, this 1 square plus 1 square is how much? 2.
Tan alpha is s by root 2 and cos alpha is root 2 by 2 plus s square.
Cos alpha is root over 2 plus this one you take. So, this is same as this. So, this one you take same as this one. So, then cos alpha is this one will be how much? Root 2, and this one is, see, this is root over 1 plus s square. So, if you take this as similar to this, cos alpha is this by this.
Sir, then what is tan alpha? Batter.
So, batter.
So one side is 2, other side is s. So diagonally. So one side is root 2, other is s. So diagonal is root 2 square, that is 2.
So that 2 will not be equal.
S square.
Two sides.
This is taken some approximate value. So, he has taken this as 1 1. If you take this as 1 1 1. So, you are saying that this will be root 2. This one.
So no, sir. The base is root 2.
Diagonal is root 2.
Yeah.
If you take this as 1, you take this as a rectangle or a square. So, this will be square root of 1 plus 1, this will be 2, root over 2. And this one he is saying that he is taking this as a square plus 1 square, square of this. And all these are similar, he is saying. Only this is vertical, S is vertical, and these are same but inclined. This one, and this one. So, this one you calculate how much? This is root over 1 plus s square. So, this is also root over 1 plus s square. So, now you find out cos alpha root over 2 by this.
2 plus s square and alpha is angle made by the
Alpha is this angle with the horizontal.
that line, horizontal line is root 2 line.
Yeah, horizontal right is root 2 line.
Then tan alpha, cos alpha will be root 2 by and that line p, that solid line length.
Yeah.
That solid line length is root
Cos
over
alpha is root 2
by
by
solid
this
line length.
this one. So, this one is 1 plus s square.
Set 2 plus s square. It will say
S
this
is
is
right angle.
Sir,
S
right
is
angle
8 no sir. Root of
those
So,
two sides will not be equal.
you are saying that this one and this one you are taking. Yeah, that also, but then again this.
1 plus s square is 65 sir. Root 65 sir.
Anyway, this.
Root 66 approximately equal.
So, this is how much then? 1 plus s square.
Root 65 sir. And actual thing is root 66. So approximately equal.
Approximately. So, that is why he has made, first of all, he has made an approximation here. This 1 1 1 1 is taking this as better. So, this is more or less same, isn't it? Anyway, so let us see. So, how much you are saying? How much this will be?
Say cos alpha equal to root 2 by 2 plus s square.
So, cos alpha is root over
2 by
2 by
2 root over 2 plus s square.
Under root 2 plus
this will be
square.
2 plus
S square.
2 plus a square. But this 2 is coming from where? Instead of 1 you are getting.
So that is root 2 by 66.
Oh, achha, this is square root over 1 plus 1 you are doing, no? So 1 plus 1 is becoming root 2 only.
So those two sides will not be equal. That one, that solid line and that dotted line.
Dotted lines will be equal.
Yeah. You are saying that this will not be equal to this.
Yeah, exactly.
But this how you are finding out. So from here this will be tan alpha you are saying, no?
Yeah.
Tan alpha will be s over root 2. So you can find out from here tan alpha is S over root 2. So from here what we are finding out? The better angle. Anyway, so you try to find out this, but then what is this P max? Or all these things you have to find out. So alpha, how much we are getting from this? I say S is given as 8. So tan alpha according to your calculation, this is 8 over root 2. So better angle is coming. Actually better angle they don't tell it like this. So alpha is coming as how much? 17? 79.97. So how much is that? This is your degrees, no? So approximately you are getting this as 80 degrees. I think this 80 degrees is more or less right. So that means slant is not much. And from here cos alpha, if I take this, from how much you are getting from this equation? So better angle is coming out to be 80 degrees. Cos alpha is how much?
Sir, if you take this formula,
This one.
79.89. This thing.
So from here alpha you are getting 79.89. So almost same. Anyway, so use this, since this you are able to understand better. So this is your better angle. Better angle is almost 80 degrees. Okay. Now P max you calculate. Now if you want to calculate P max, so you start from P1. So this is how much? So this is P1. P1 is going vertically up. Okay. So P1 cos of 90 degree minus alpha. So this is going vertical. So this is 90 cos of 90 degree minus alpha. This is P1 sin alpha. Okay. This is P1 sin alpha, and next you take components both from your vertical P1 and the horizontal VH. So VH, how much you are getting? So and both will be in the same direction, mind you. So this is plus VH cos alpha, isn't it? Am I right? So this is your P max. See how much it comes.
So P max equal to P1 sin alpha or P1 by sin alpha?
P1 by?
Sin alpha. Because P max sin alpha equal to P1.
No, this see you take P1 is going, you take like this, take component on the this axis. So this will be P1 cos of this angle, no? So this angle is 90 degree minus alpha. P1 cos 90 degree sin alpha only.
P max cos alpha should be equal to P1.
No, you don't go from, you calculate P max. You take components from P1.
Calculating P max. So P max. So you are taking components along vertical and horizontal.
Yeah. Further, you take component like this, component coming from P1 and component coming from VH. You add those two. तो ठीक है? So P1 cos alpha will be from here and VH is coming here. You add those two, vectorially it is added. See how much it comes. And next you calculate V. So this is your maximum what? This is maximum axial force. and if you calculate V, you will get maximum shear force. Batter angle is 80 degree. Now P1, how much we have calculated P1? P1 was 4194. So how much, anyway, how much you are getting? P1 was 4194 and VH that we have calculated was how much? 1600, no? No, there is 1600 by 4. 4 piles were there. So how much it is coming? I have lost that page. Now shear is how much coming component from VH?
P1 cos alpha minus VH sin alpha.
P1
P1 cos alpha
cos alpha
minus VH sin alpha.
VH sin alpha. So how much we are getting?
Four thousand
4,200. So this is okay. 4,200 kilopounds. The other one? 337 kips. But this is in which direction? In this direction or this direction? This direction. Anyway, so this is a calculation of your maximum axial force and what else? Shear. Now piles, actually you will find there are other important pile stresses. First you calculate axial, then what we have calculated? Shear, and last one you need to calculate is bending. So these are the three important stresses coming on the offshore pile. Now this bending stress, how you are going to calculate? So this you have to calculate from sigma is equals to m divided by what? I by y. M is your bending moment at a particular section and this is your section modulus. Now, this we have to calculate, but before we go into this, this is quite complicated stuff. So, this is built. Now, the function of the pile, you write pile calculation now in the formula for this bending you have to have a relation between what? Relation between soil modulus of elasticity. Now, actually this type of calculation you are not familiar with, because most of you are familiar with the buoyancy calculations. Now, pile the scantlings, if you want to calculate, you have to formulate a relation between soil modulus of elasticity and what? And rigidity modulus of pile material, or rather you can write pile cross section. Now, this has to be found out. Now, if you want to do this, then you have to have a definition of soil modulus. Soil modulus is defined as ES is equals to minus P over Y. Now, this Y is not the axial deflection, this is the horizontal deflection. Now, this we will try to find out. Now, before we go into this, there are certain assumptions that is required. Now, in our case, offshore piles. Now, what I am teaching you is a very simple calculation. If you go in offshore, you will find all combinations of loading that I have told you. So, offshore pile foundation we have calculated the axial. This thing was, you find out a check from this, and here actually the maximum load is coming from the waves. So, you have to find a solution for laterally loaded piles. This type of piles are called laterally loaded piles. Now, we are studying single piles only. That means we are not calculating pile groups, but you will find those towers, the platforms which are very large, they are called offshore towers. Now, towers actually they are going to say 500, 600 meters of water. You cannot drive piles through the corner columns because they will be too long. Now, what is normally done is you drive piles on the periphery of the columns. So, this is your say batter pile. So, batter angle we have calculated as 80 degree. Now, there will be pile sleeves like this. Now, through these you insert piles. You cannot insert main column piles through this, because this will be of the order of say 500, 600 meters. So, normally this is the case, and this is called skirt piles. Now, this type of piles if you want to study, then this whole thing is a pile group. And these piles are driven below the water surface. So, this is your water surface, you have to drive piles in this mode. This is called underwater pile hammers. So, you can see that this type of civil engineering job or structural engineering job is dangerous. So, underwater pile hammers. Very easy to drive piles from the above the sea surface or mean sea level, but here actually a problem will be there. So, this is called a pile group. Now, pile group, when you want to study the mechanics will be slightly different, because one pile will be interacting with another, because your soil is getting compacted and some soil will be pushed out and all these things will happen. So, this is called a pile groups. Normally, if you in civil engineering, all these foundation piles, if you see, they also have pile groups, but they are not arranged in this fashion. They are more or less arranged vertically. In your case, this is going to have a slant or a batter, and at the top you will find, so this is a pile group. So, this is driven inside the soil. This is your soil. This is, you can see this is your soil. So, this is a pile group, and at the head this is called pile cap. Now, you build a structure on the pile cap, isn't it? Now, this is the normal case for a building. A building pile foundation will have something like this, and all this the structure will come. So, you make a pile cap. Similarly, in the bridge piers that you go in the bridges, you will find the bridge pier is also on a pile cap like this, the bridge pier. Why? Bridge is also, you will find your pile cap normally you cannot see, which is under the river bed. So, this is will get eroded. That is why you make a foundation like this on pile cap. The pier is always built on piles. You will never find a pier or just sitting on the seabed. You cannot see on the river bed. You cannot see with your open naked eyes, but at below the river bed you will find huge piles. So, you have to make a foundation strong. Now, here actually in the sea, open ocean, the problem is much more, because the surface you will have waves, then you will have large current. So, Gujarat coast is having current of 7 knots. So, huge current will be there, then you have mudslides. So, all this has to be catered. So, that means these cut piles are also quite long, and to drive number of piles. So, anyway, so this is the scenario, and now in the simplest analysis, let us study for a single laterally loaded pile. That means, when you come to this section modulus calculation that I have just now talked, that ES, where was that ES? Yeah, this. So, if this was your case, that means you will find the pile will get deflected. So, this is your seabed. So, this is the pile. Now, why this negative sign is coming? So, in my calculation I have given a negative sign. section modulus calculation. Your pile is going to bend like this. So, let us say that this is your center line. There are two things you have to study. One is the force that is coming from the soil. Now, you take, say you apply a force, say this is your y direction and this is the direction of x. This is the direction of x and you are giving a lateral load. So, that means P is horizontal and this is your seabed. Okay. So, obviously, if you push the pile in this direction, your soil is going to exert a opposite force in the reverse direction. Now, as you go deeper down, you will find that this force is decreasing, because at this is normally called a pile head. This is called a pile head. Now, if you push the pile in the right hand side, you will be pushing more soil at the surface, but if you go deeper down, you will find lesser soil will be shifted. So, that means at this region you will find the maximum force. So, this is the distribution of the force from the soil, it is coming in this direction, and then again it is going to be reversed. Anyway, now your pile deflection also will come somewhere like this. This is your pile deflection. So, ours is a elastic steel pile. There are other types of piles also which we are not studying. So, this is the case of a elastic steel pile. In the present scenario. Now, offshore structures, when they were first constructed, they were in shallow water, then we had wooden piles. But now, of course, we have gone to hundreds of meters, so there is no point in having a wooden pile. So, in this diagram you can see, if the direction of force is in this direction, then the deflection is in the opposite direction. So, that is why you give a negative sign. So, ES is minus P by Y. This is coming from that P is equal to Kx formula, straight. From that you can calculate. Now, this is called the soil modulus. So, we will come back to this again, but before we make the analysis, there are certain assumptions we should be careful about. One of the assumptions is, so this is solution for laterally loaded piles, and number 1 is B, laterally loaded piles. Now, in offshore actually we will find that most of the piles will have a batter. Now, what we will study is without batter in the simplest case. So, laterally loaded piles are elastic members. So, we are not making analysis in the plastic zone. Normally, failure of offshore structures, you make a what is called a elastoplastic analysis. I do not know whether you have come across this term in failure, when you go in the failure mode actually. So, anyway, we forget about that. So, we assume this to be elastic. The other assumption is soil. Soil is also assumed as elastic. Otherwise, that ES is equals to minus P by Y you will not get. theory of subgrade action. What is this theory of subgrade action? So, I told you that means we have to strike a relation between ES, basically you have to strike a reaction between ES and EI. Somewhere I have told you this. So, relation between ES and EI. You have to find out this. So, that is called subgrade action. We are not taking any, there is no axial load. So, that means the analysis that we are going to do right now is very simple. Simply you take a lateral load. Now, two types of piles are there. One, we write long piles. The other is called short piles. Now, this short pile category is, it behaves as a rigid body. Behaves and rotates as rigid body. And this one is deflects along length. So, there is pile, this actually I do not know why the short piles we are not considering, we are considering the long piles. Now, long piles you will find that after a certain length of pile it becomes redundant. So, that means there is no pile load, all pile load is taken up by a particular length of pile, as I have given in that equation, that friction and bearing equation that we have started out with. So, once all the load is taken over, then the length becomes redundant. Now, laterally loaded piles, there are three types. One is called a free head pile. The other one is called fixed head pile. The pile head I have already defined, that is where it is entering the soil. And the last category is called a partially restrained pile head. Now, offshore piles belong to the third category. So, your offshore piles are partially restrained. What is a restraint? When you are talking about free and fixed head, then obviously there is a question of restraint is coming. So, that means it is not free to rotate or getting displaced. So, that is called a partial you are under partial restraint. This is coming from where? This is from jacket. Now, jacket is giving you the restraint. that is limiting the horizontal displacement and rotation. So, that is your restraint is coming. So, this is coming from offshore piles. Now, we have to find out this, find deflection. Now, this we have already, same thing we have done for hull girder bending, slope, sorry, moment, bending moment. Then calculate shear, soil reaction. Now, this method has been devised by a person called Rees and Matlock, and there are a number of solutions to the equation. Now, the one that we are going to study is the non-dimensional method. Now, that corner pile calculation that you have made is only for a single pile. So, solutions are, number one, you will get closed form solution. Number two is difference equation. The third one is non-dimensional method. There are other methods are there. This is called the PY curve, etc., and all these things. So, we will study this one only, non-dimensional method. Now, if you want to study this, you first assume the pile to be a beam. Say this is our pile. We are considering only a single vertical pile. Say this is a single vertical pile and this is your pile tip. Now, you take the x direction to go vertically down and the y direction to be on the soil. So, pile force is coming here on the seabed. So, this you mark this as capital P, or rather you write PT. Now, you are going to get another moment out here. This is MT, and this is your ocean bed. So, you try to analyze like this. Now, this I have told you, your jacket column is coming like this. Okay. Now, this is your seabed and this is your wave. So, you transfer this force to here. You find an equivalent force and moment. If you replace this, so there will be, if the force is acting at the waterline, say this is PT. So, you obviously you make a equal force if you want to find a force. So, this will give you a moment like this and a force in this direction. You transfer this force at pile head. You transfer this force at pile head, you will get PT and MT. Now you study your deflection. So the deflected nature of the pile will be, I am just drawing one vertical line, okay. Now what we have to find out, your pile is going to bend like this. So this is your Y. Now in offshore actually there are two things. One we are interested is, I told you that our calculation was bending stress. We have found out the axial and shear. So that is important, and you have to find out the bending stress from this and pile deflection. Now sometimes most of the regulatory bodies, they put a limit on this Y. Okay. Now that means we have to find out this value of Y from your slope. So you write down the slope equation. So in that ship girder problem, how we started out, you remember? The same procedure you adopt here. Your slope is along this line. So this is your S equals to dy dx.
So this will not be vertical.
Is a vertical pile.
Slanted.
Slanted we are not considering right now. Slanted, that means you have to take the projection and do this. So battered piles, those are called battered piles. So let us study the simplest vertically loaded pile. There is no, I have not given any axial load also. This is just your, say, moment that is coming from the waves. So you have taken this at the seabed. Obviously at the seabed you get one force and a moment. If you take equivalent force, you put equal to P this side, so you get a force in this side, and this couple will be turning, isn't it? So that is how you get a equivalent force and moment. So you calculate Y from this is the deflection, this is slope. So you integrate the slope curve, you get your deflection. And how do you get this slope curve? So this beam bending formula, if you remember. So we worked out an equation where you calculated the hull girder slope. So bending moment equation. Now here you find this rigidity modulus coming in to your calculation. So this EY, what is the formula? You remember this? Next, so this is your moment, bending moment rather. So you have to calculate shear. So shear also you will get EI. So EI is your modulus of rigidity d cube y divided by dx cube. Last one is the P1, the load. So this is going to vary like this. So, integration of the soil reaction will give you shear, you integrate shear, you get bending moment, integrate bending moment gets slope, integration of slope will give you deflection. The same procedure that we have followed for the Hallgada bending, but here actually you will find that this trouble is with ES. ES is called the soil modulus. Now, ES varies with pile diameter. Then you have soil properties. So, this actually you have to find out from your lab experiment. Nature of loading. See, all this you have to control. Now, working with soil is different from working with water, and the other one is EI. EI is called flexural stiffness or flexural rigidity. Of pile material. So, these are some of the values which you have to find out. So, it is not an easy job. The thing that you can do is you strike a equation, and ES is normally given in this form. This is NH into x to the power n. Now, NH is called coefficient of soil modulus. Variation. So, this you can say, and the other is the n, this power. X is already what? X is your pile depth. That is, you have taken x along this axis. This is your x. Now, this n, the power, you take as either half or 2. Half, 1, 2. So, this is your power. Now, n equal to 1 is for granular soils. So, normally you take n equal to granular soils means sand. Now, in a general case you take this equation. So, any problem with pile foundation, this NH and N has to be specified. So, any is this you be given in a table, so you need not worry about this. And the other part, so coming to the calculation, that is your non-dimensional solution. You write pile deflection in this form. Say function of x, t is, I will tell you what is this t, L is L. Now, all these are non-dimensional. Now, ES is the subgrade modulus from soil, EI is your rigidity modulus. PT is what? The horizontal force coming at the pile head. MT is the overturning moment at pile head. So, this is your non-dimensional equation, and deflection you write y equals to YA plus YB. YA is deflection, due to PT, that is horizontal load. So, there will be actually two deflections, one coming from the horizontal load and YB is coming from the moment. So, these are the things which you have to find out. So, we are doing non-dimensional, so that means you non-dimensionalize depth. Then what is T? T is called the relative stiffness factor. Now, here that NH term will come. This is to the power 1 divided by n plus 4. Now, remember this n and NH is different. So, that is called a relative stiffness factor. So, here actually this T is a term which links your pile modulus of rigidity with the soil, that ES is coming. So, this is one. Then the other is the depth coefficient we have already defined. So, maximum depth coefficient. So, what is the value of this? Z max. If this is your definition for Z, where X is the depth of pile, so obviously Z max will be the total length of pile, that is given by L divided by T. So, that is called the maximum depth coefficient. Then you have soil modulus function. So, you can see that with a single pile we are having so much of equations. So, that is termed as phi of Z. This is given by your soil modulus ES multiplied by the rigidity modulus, that is T to the power 4 divided by EI. Then you have deflection coefficient. Now, remember there are two types of deflection we are considering, that is one caused by the horizontal load, that is your YA. So, this is called deflection coefficient. AY. So, this is YA into EI over now this is what type of deflection? Deflection that is coming from PT. So, obviously, this will be a displacement. Now, there will be another type of deflection. This is given as YB. So, instead of PT, this will be MT and the T square will come. So, all these are non-dimensional terms. You just because we are doing non-dimensional analysis. Now, this will give what? So, pile head is having both lateral displacement as well as a rotation. Now, you have to find out these two. So, that is the main job. Now, ES equation that I have already given you, you use that. So, this is your NH x to the power n. Now, the main exercise will be you calculate these values, this Y, S, M, V and P from these non-dimensional parameters. Then your job is complete. So, you will work out next class since you want to go. So, Thursday afternoon all of you are free.